Welcome. In this session, we'll learn the concept of time constants in circuits. Let's start. Now, in the previous sessions, we learned what happens to the capacitor voltage and inductor current when we connect a source to these RC and RL networks. All right, we learned how the capacitor voltage and inductor current behaves. Now, what I'm saying, when we connect a source to a RC circuit, and if we connect to this at t equal to 0, this is the supply voltage. How the capacitor voltage behaves. The capacitor voltage is given as Vc of t is equal to Vs E1 e to the power of minus t by Rc. Same way, if we have an RL network, and if we connect to this network to a source Vs at t equal to 0, how the inductor current behaves, right? We know the inductor current is given by I of t is equal to Vs by R 1 minus e to the power of minus t by, this is minus R by L t. All right, so this is the behavior of the capacitor voltage in RC circuit, and this is the behavior of inductor current in RL network. Now what we are going to do, if we put tau is equal to RC in this, and if we put tau is equal to L by R in this, what we are going to obtain? We are going to obtain Vc of t is equal to Vs 1 minus e to the power of t by tau, and I of t in this RL network will be Vs divided by R 1 minus e to the power of minus t by tau. So this is the capacitor voltage, and this is the inductor current when we connect a source to RL and RC networks respectively. All right. Now, what is this tau in RC circuit? First, let's talk about this. What is this tau? Tau is a constant, circuit constant, and is referred as the time constant of this RC circuit. This is referred as the time constant, and it has the units of time, that is seconds, milliseconds, and so on. Similarly, tau in RL network is simply L by R, and it has the units of seconds and is referred as the time constant of RL network. So this is a time constant of RL network. All right. So now what we have obtained, Vc of t is equal to Vs 1 minus t by tau. So let me write tau like this, where tau is RC, and this is referred as the time constant of the circuit. Now, if we plot this expression, we saw the plot in the previous classes, but let's do that again. So this is Vc of t, and let's suppose this is V of s. This is a constant value, that is V of s. Now, if we plot this, now at t equal to 0, this expression is 0, so the capacitor voltage is 0. At t equal to, as t increases, and it increases towards infinity, as t will reach to some value. Let's suppose it's equal to tau. What's the value of this expression? Now, if we see the value of this expression at tau, means when t is equal to tau, this will be Vs 1 minus e to the power of minus 1, because it will be tau divided by tau, and that's equal to minus 1, and this will be equal to Vs 1 minus what is e to the power of -1? 3679, and that's equal to, this is equal to 0.6321 times Vs. Means when t is equal to tau, and tau is the time constant. When the time reaches equal to one time constant, the capacitor voltage reaches to the 63%, 62.1% to be exact of the final value. Means in time, one time constant, the capacitor voltage rises to almost here, that is equal to 63.21% of this final value of this capacitor voltage. Similarly, as we increase, as t increases to 2t, 2 tau, 3 tau, 4 tau, 5 tau, and so on, and so will the capacitor voltage rise. Now, as if we substitute t equal to 5 tau, if we put one specific value, t is equal to 5 tau, so what will be the voltage at capacitor voltage at this time? So it will be Vs 1 minus e to the power of, so if we substitute here t equal to 5 tau, it will be e to the power of -5. So if we substitute this will be simply Vs 1 minus 0.0067. I hope I'm right. So this will be equal to 99.9933 Vs. Now what is this saying? Means the capacitor voltage rises to the 99.33% of the Vs. What's Vs? Vs is the final value that this capacitor voltage acquires. So in 5 time constant, the capacitor voltage rises to the 99.3% of the final value. So what I am saying, if we plot this capacitor voltage, it rises like this, means this behavior is exponential behavior, and it finally reaches to this V of S, means the battery voltage, and the voltage rises to almost to the 99.99% of the final value, means final value is the battery voltage, that is in 5 time constant, it almost reaches to the this. All right, because 99% we can take it is the final value. So in 1 time constant, it reaches to the 63% of this time. So if we say this is the tau, from this to this is tau. So in this time, it reaches to 63.63% times Vs. All right, so means 63% of the final value. Now in 5 time constant, if I say this is the 5 time constant, means from this to this is time is 5 time constant. So in this time, the capacitor voltage rises to the 99.3% of the final value. Final value is the Rs. And what's tau, by the way? Tau is the RC. That's why in the earlier class I told you how fast this rise will be, means how fast it will rise to this Vs voltage. How fast? It is determined by this R and C. What is the parameter value of this R and? What are the values of this parameter? Parameters R and C. All right. So in 1 time constant, what is time constant? For RC circuit, time constant is equal to RC. So in 1 time constant, it reaches to the 63% of the final value of this. And similarly, in this 5 time constants, the capacitor voltage rises to the 99% of the final value. All right, let's talk about now inductor circuit, inductor RL network. Let's talk about inductor. All right, RL network. All right, let's talk about RL network. So in RL network, what we have the current that flows there is Vs divided by R 1 minus e to the power of t by tau. And what's tau equal to for RL network? It's equal to L by R. It has the units of time. So this is referred as the time constant of RL network. And if we see the behavior of this current, in other words, if we plot this current, inductor current, and if we suppose this is Vs by R, because this will be the final value of the current. As t approaches to infinity, this term is 0. So the final value will be Vs by R. So this is the plot of this. Now, if we check the value of the current for different values of t, and let's suppose some specific value. At t equal to 0, you can see at t equal to 0 means when time is equal to 0, this quantity is equal to 1, so this will be 0. So the current at t equal to 0 is 0. Now at t equal to tau, means when t is equal to the one-time constant, what is the value of this inductor current? Now from this inductor current, you can see it will be Vs by R times 1 minus e to the power of, it will be tau divided by tau. So that's equal to -1. And if you evaluate this, it will be again 0.6321 Vs by R. That is same as 63.21% of Vs by R, means this will reach to the 63.21% of the final value. What is the final value of the current? Vs by R in this circuit. In this circuit, the final value of the current will be Vs by R, means the current will finally rise to Vs by R value. So in one time constant, the inductor current will rise to the 63% of that value. Now, similarly, as t increases to 2 tau, 3 tau, 4 tau, 5 tau, and so on. Now, if we substitute one specific value, and that is when t is equal to 5 tau, inductor current will be equal to Vs by R 1 minus e to the power of -5, and that's equal to 99.9933 Vs by R. Vs by R will be some value, so that means it will be 99.33% of Vs by R. Means in 5 time constants, the inductor current will almost rise to the 99.33% of the Vs by R. And what's Vs by R? Is the final value. So as the capacitor voltage rises, inductor current rises like this, and finally reaches to Vs by R, and in one time constant, the the inductor current rises to the 0.63 times Vs by R. And in 5 time constants, if this is tau, then this is 5 tau. So it will reach to almost to the 99% of the final value, and that's almost this. So in 5 time constants, it rises almost to the final value of the current, that is Vs by R. So in other words, whether it is RC or RL, we can say both the values, means whether it is capacitor voltage or inductor current, the voltage rise in 5 time constants, the voltage almost reaches to the final value, right? What is the final value of capacitor voltage? It is V of S. What's the final value of the inductor current here? It is Vs by R. All right. So in 5 time constants, it reaches to the final value, almost. Although the value is not exact, it will reach to the mathematically it takes almost infinite time. But ideally, you can say it reaches to 99.3%. You can take it that's equal to the 100% of the final value. Now, this is as far as the charging is concerned. Now, what about the discharging circuits? When we said the capacitor was charged to some voltage, our inductor is having some initial value of the current. So, in other words, what we are saying, if we say this is the RC circuit, and this capacitor is having some initial voltage, means Vc of t is equal to some voltage V0 at t equal to 0. All right, this is having some initial voltage. And what is the behavior of this voltage? We saw it, we derived it. It is equal to Vc is equal to V0 e to the power of t by RC. Same way for an RL network. If this is an RL network, and if we say this is I of t, so I of t, and we say inductor is having some initial value of the current, that is I naught. So at t equal to 0, this is the value of the current. Then the inductor current behaves like this. It is equal to I naught e to the power of minus. This is equal to R by L T. We derived in the last class. So we can write it like this. If we replace RC is equal to tau in RC circuit, and L by R is equal to tau in RL network. Okay, source free means there is no source. So we can write the Vc of t is equal to V naught e to the power of minus t by tau. And we can write the inductor current like this, I naught e to the power of minus t by tau. All right. So this is the capacitor voltage, and this is the inductor current in source-free networks. Means and there is no source connected. Only thing is capacitor is having some initial voltage, and inductor is having some initial current. Okay, this is the behavior. Now, if you plot these, this, let's do the plot first for the capacitor voltage. So the capacitor voltage. So at t equal to 0, it is having some value. How much? If you put t equal to 0, the voltage value will be V naught, because that's what we assumed. And from this equation, you can confirm e to the power of minus t by tau will be equal to 1. All right. Now at t equal to tau, how much is the voltage of the capacitor? So in one time constant, it will be V naught e to the power of minus 1 from this expression. Tau and tau will cancel, it will be e to the power of minus 1. So that's equal to, what will be this? This is equal to 0.3679 V naught. In other words, this is equal to 36.79% of V naught. 36.79% of V naught, or in other words, if you assume this is equivalent to 37% V naught. In other words, in one time constant, the capacitor voltage decreases to the 37% of the initial value. Means capacitor voltage is dropping to almost to 37% in one time constant. Similarly, as time increases, and let's take one specific example. If we say t is equal to tau, so what's the value of the capacitor voltage in 5 time constants? It will be V e to the power of, if you substitute it in this expression, t is equal to 5 tau, it will be e to the power of minus 5. And if you substitute this will be almost 0.0067 V naught, and this is almost equal to 0. So in other words, means 0% or 0% of V naught. V naught is the initial value. So in 5 time constant, the capacitor voltage almost drops to the 0. So if you plot this like this, so in one time constant, if you see this is the one time, this is tau. So in one time constant, the capacitor voltage drops to the 0.37 V naught, although it's actually 0.3679, and we are assuming that's approximately equal to 0.37. So it drops to the 37% in one time, and in 5 time constants, the capacitor voltage drops to almost 0 here. You can check it, it drops almost 0. Actually, the actual value is 0.0067 times V naught. All right. So in 5 time constants, this source P RC capacitor voltage drops to almost 0 in 5 time constants. Same way, if we plot the inductor current, means source free inductor current, when there is no source connected in the this RL network, and we are assuming only that this is having some initial value I naught. Now if you take the plot of this expression, what is the value of the current, means inductor current at t equal to 0, the value is I naught. You can check it from this expression. At t equal to tau, what is the value of inductor current? Means I of tau will be equal to now I naught e to the power of minus 1, because tau and tau will cancel, because t is equal to tau, it will cancel. So it will be this, that's equal to 0.3679 times I naught. And you can say this is approximately 0.37 I naught point. So that, in other words, means this approximately drops to the 37% of the initial value, means the value in one time constant of the inductor current is almost here. If you say this is 0.36 or 37 times I naught. All right, so this is the inductor current. Now at t equal to 5 time constants, what's the inductor current? So I at t equal to 5 time constant, it will be I naught e to the power of -5. So that's equal to 0.0067. I hope I'm right, 67 times I naught. So that's approximately equal to 0. This is approximately equal to 0. So in 5 time constant, if you say this is tau, and then this is 5 time constant. So in 5 time constants, the inductor current almost drops to 0 here. Okay, so it drops to 0. All right, I hope you have got the idea of this time constant. So this charging, how fast it charges and how fast it discharges in both RC and RL networks is governed by that time constant. And for an RC circuit, the time constant is equal to RC, and for RL network, the time constant is simply L by R. Okay, both are having the units of time, milliseconds or milliseconds, whatever is the unit of time. And please have a look at this notes how we plotted the capacitor voltage and inductor current, both in charging and discharging case. And what's meant by one time constant, 5 time constant, both during time, charging and discharging case. Now let me repeat the whole thing again. Now if I talk about the capacitor voltage, and the expression during charging looks like this. Now in one time constant, the capacitor voltage rises to almost 63% of the final value. And in 5 time constant, the capacitor voltage reaches to 99% of the final value. If you take that, that's approximately equal to the final value. So we say approximately the capacitor reaches to the final value in 5 time constants. All right, and time constant for RC circuit is equal to RC. So now the inductor current is governed by this expression. If we have a voltage source in inductor, remember that if we have voltage source as the source in this inductor. All right, so have a look at this. Now in time constant of this circuit is L by R. In one time constant, the inductor current rises again to the 63% of its final value, and in 5 time constants, it reaches approximately to the 99% of the final value. And we say, for practical purposes, we say the capacitor current finally reaches to the final value in 5 time constants. Now, if we are talking about the discharging now, means if we say discharging circuits, means whether it's RC or RL circuit. If the circuit is RL, if the circuit is RC, let's take that. And if we say the initial voltage stored in the capacitor is V0, then we know the behavior of the capacitor voltage will be like this. When it is source free means when there is no voltage source or current source connected to this source. And in other words, this will give us the discharging behavior. Again, the time constant will be in this RC source free circuit will be RC, and it will behave like this. And in one time constant, again, it will drop, the capacitor voltage will drop to the 37% of its initial value. Means in one time constant in source free RC circuit, the capacitor voltage drops to the 37% of its initial value. And in 5 time constants, approximately the capacitor voltage is equal to 0. And same thing is true for a source free RL network, means when there is no source connected in the RL network, and this gives us the discharging behavior of this inductor. And if we assume the initial current at t equal to 0 is I naught, the behavior is governed by this expression. And again, the time constant of the circuit is L by R. So if we see the behavior of this expression, it looks like this. And if we plot it with respect to t, and if we take the examples, a few examples like t is equal to 0, t is equal to tau, t is equal to 5 tau time, you will see that in one time constant, it drops to the almost to the 37% of its initial value, means the inductor current drops to the 37% of its initial value. Same way, it drops to almost zero, means the inductor current becomes almost zero in 5-time constants in source-free RL network. I hope you have got the idea of this time constant in RC and RL networks. In the next session, what we are going to do, we are going to learn these concepts in MATLAB. How do we plot these responses in MATLAB? And I will teach you there, what do you mean by this time constant there. All right, okay, let me end this session here.